Hello and welcome to the fifth lecture. In our previous lectures, we introduced the concept of visual augmented and extended reality. We also learned something about industrial training and maintenance, and we introduced the main concepts of input and output XR technologies. In this fifth lecture, we'll focus on two sensory modalities that can be exploited to make interaction with simulated environments more natural, complete, intuitive, and so on. At the end of this fifth lecture, you will learn the basic principles behind technologies for the sense of touch and for the sense of smell, how to integrate these technologies to make interaction with virtual worlds more natural, and finally some tricks that will allow you to overcome any limitations of these technologies. So I have worked with visual and augmented reality technologies for 20 years now, and I have experienced the same scene many times. When you start exploring a visual reality environment, at a certain point it is natural for you to try to interact with the objects in the scene. You want to grab them, move, touch, and feel them. These objects can be made interactive using, for example, hand tracking, so that the user can pick them up, move them, and manipulate them. However, when you grab the object and move it by simply using a tracking system as an input device, you suddenly realize that this interaction is missing something to make it more realistic, and that this is the component of the sense of touch. You interact with the object, but you cannot feel it. For example, imagine using a simulation that has the purpose of teaching you how to assemble an industrial product. You're asked to take some components, move them to the right position, and assemble them. This is the simplest assembly simulation that we can imagine. In this case, the absence of the sense of touch does not allow you to feel the weight of the objects, their temperature, the material they are made on, and any collision between objects. The action of assembling different components loses a lot of information when you're deprived of the sense of touch. It doesn't seem natural. The movement you make might also be affected because of this simplification. Fortunately, there are extended reality technologies on the market and in several research laboratories that allow us to exploit the sense of touch. These technologies are called haptic technologies. When we think of the sense of touch, one of the first images that comes to our mind is the hand, which is a very complex and fascinating organ when we start studying it. However, the sense of touch is not limited to the hand, but is distributed on the entire body. If I touch your face or your arm, you can feel it. So if we design a visual interface, we focus on the eyes. And for audio interfaces, we focus on the ears. For the sense of touch, we need to decide which part of the body will be involved in the interaction, since at the current stage, it's difficult to imagine a technology able to covering the entire body and communicating correctly. Let's try to focus only on the hand for simplicity in this lecture, neglecting the rest of the body covered by the skin. And let's also forget that the hand is a configuration that changes continuously as we interact with the object around us. Suppose we want to make the user feel the contact with a virtual object in a virtual reality environment. The first thing to understand is where the user's hand is located in relation to the virtual object he wants to touch. Then, as the hand moves, we need to understand if there is a contact. Once we have established that there is a contact, we need to reproduce a sensation of contact that is realistic and that updates in real time if something changes. For example, imagine if you are touching a virtual ball and the ball moves when we touch it. In practice, communicating through the sense of touch, in this case, means tracking the position of the hand through tracking technologies, understanding if there is a collision, reproducing a realistic tactile sensation thanks to output technologies and an appropriate control. It comes out that, according to the classification we have seen in the previous lectures, a haptic interface is both an input and an output device. According to a classification traditionally adopted in the scientific community on the sense of touch, haptic technologies are divided into large categories: force feedback technologies and tactile technologies. This classification means that the first one communicates forces while the latter conveys sensation through the skin. Although this classification is quite old and can be updated, of course, it describes the two micro-categories of technologies that we can find on the market. Some force feedback technologies have structures that resemble industrial robots. They have been designed, for example, to allow the simulation of assembly operations in which it was essential to feel the weight of objects and possible collisions. Their dimensions vary according to the workspace needed for the simulation, and they differ also in the force return to the user hand and the degrees of freedom that they can reproduce. They also differ in terms of mechanical design and control. On the other hand, there are technologies such as those integrated into mobile devices that allow interaction with visual buttons through glass by using simple vibrations. There are also glove-shaped haptic interfaces, which integrate actuators inside them that communicate through the use of vibrations, small skin pressures, and temperature changes. So choosing the right technologies to use in a given application is challenging. It is necessary to start from the component of the tactile sensation that is necessary to represent in that type of application. For example, where is a question of small skin pressures or large forces, whether the thermal component is necessary or not, the working volume to be covered, and so on. Finally, it is important to integrate the tactile component of the interaction with other senses coherently. Sometimes we can even compensate for the limits of this technology by acting on other senses. You learn these basic rules only when you start developing application in a continuous testing and tuning loop. Then there is another sense that plays a fundamental role in everyday life and can be integrated into a visual simulation, and it is the sense of smell. Let's think, for example, about the importance that this sense has in allowing us to identify some dangerous substances or fires. Its use in the context of simulation for industrial training would be very useful, but the available technologies are still few and not as ready as those for the sense of sight. Fortunately, both in the scientific field and on the market, technologies that can be integrated with virtual reality environments are beginning to appear. The sense of smell presents the following challenges: identifying some basic scents that are suitable for the scene we want to represent, designing the right technology to send these scents to the user nose when needed and remove them where they are no more necessary. Ensure that this happens in real time in a scene that, by definition, is dynamic. Since there is no technology that we can define as the ultimate technology, sometimes it is necessary to design your own technology, as we did it in the past. We understood that introducing new sensory modalities is not that immediate, but introduces new challenges. At the same time, we have seen that adding one or more senses can increase the number of possible uses of extended reality.